Alright, so the next type of transformations that impact outputs y are what we call vertical stretch or compressions. What you'll notice for this particular examples, we're no longer adding or subtracting, right? We're not adding something to x or subtracting something to x, moving things left or right. We're not adding or subtracting something to the x squared, moving it up and down. What we're now doing is taking the output x squared and we're now multiplying it by something. So there's a multiplication going on. So when we multiply to an output, we create either a stretch, so that's going to take my graph and make it longer vertically, or we're going to compress it. It's going to take my graph and it's going to kind of compress it down and smash it vertically. So that's what these two graphs are going to be doing. So let's take a look at each. Again, we'll do the ground and pound. We'll do some point plotting and kind of see which one does, which each one does. All right. So we get -2, -1, 0, 1, and 2. So I put a -2 in there. We get 2 times 4. We get 8. Put a -1 in there. We get 2 times 1, which is 2. Put a 0 in there. We get 2 times 0, which is 0. Put a 1 in there. We get 2 times 1, which is 2. And put a 2 in there. We get 2 times 4, which is 8 again. Alright, so there's basically our new data points if we take the outputs and multiply them by 2. So graphically, what do we see going on here? Well, again, I'm going to go to my grid. There's a graph of a basic x squared shape that has no transformations, right? A nice vertex at 0, 0. But in this case, we have a -2, 1, 2, 3, 4, 5, 6, 7, 8, way up in here, kind of into the function. Sorry about that. We've got -1 and 2. We've got 0, 0. We've got 1 and 2, and then 2 and 8, which will be up in here. So we still have the parabolic shape. The vertex actually did not change, right? The vertex is still going to 0, 0. But if you take a look, right, this graph has been stretched, right? As a matter of fact, in comparison, right, the normal graph goes through 0, 0. So it'd be out in here somewhere. So the graph, the normal graph, has been stretched out vertically. So that creates a vertical stretch. And you can say by a factor of 2 if you would. So we're going to get a stretch by a factor of 2. Alright, so what about 1/2? Well, again, if you're kind of anticipating, I'm expecting a compression here, right? The graph is going to basically compress itself. It's going to be kind of smashed. So let's just do the ground and pound work, graph the points, and see that our anticipation is right. So if I put in a -2, we get 1/2 times 4, which is 2. If I put in a -1, we get half of 1, which is 1/2. If I put a 0 in there, we're going to get a 0. If I take 1/2 of 1 squared, we're going to get half times 1, which is a half. And if I put a 2 in there, we're going to get 1/2 times 4, which is 2. So there's our data points for this graph. So when we go to our grid and graph it, right, we have -2, 2 that's on the graph. We have -1 1/2, 0, 0, 1 1/2, and 2. And so here's what this new parabola looks like when we multiply it by 1/2. Again, you can still see the vertex is 0, 0, but when we compare it to the other graph, right, it's been kind of flattened. As a matter of fact, let me kind of, here's 0, 0, 1, 1. So this graph, right, the normal graph would be right in here. So it's like somebody took that graph, right, so it would be a 1, 2, 3, 4, and 4. So here's the normal x squared graph. It's like somebody flattened it, right? We took all the y values and halved them. And so the overall effect is it's like we took this graph and we vertically compressed it. Okay? So there's basically our two ideas. So this is a vertical compression. And you can say by a factor of 1/2. All right, and kind of getting into the little future here, it turns out, how can you tell the difference? Well, if we're going to be graphing y equals ax squared, if a is larger than 1, so like 2 or 3 or 4 or 3 halves, this is going to result in a stretch. So we're going to take our normal graph and we're going to make it skinnier, if you would, stretch it out. And if the a is between 1 and 0, so it's a fraction, like a half, 3/4, 9/10, whatever the case might be, that will result in a compression. Alright, so you can kind of take that to the bank. Alrighty, so there's your introduction to another type of transformation that we can do to our basic graph to make it skinnier, if you would, or to make it look a little shorter or compressed. Alright, we multiply by some factor that's greater than 1, or we multiply by some fraction that's between 0 and 1. Things multiplied by 1 stretches it out, makes it skinnier. Fractions, right, less than 1 make us compressed. One last transformation and then we'll finally put this all together.